Hello and welcome everyone. Thank you for joining us today for our webinar titled Deep Dive into Responsible Machine Learning with H2O Driverless AI. My name is Patrick Moran. I'm on the marketing team here at H2O.ai, and I'd love to start off by introducing our speakers. Navdeep Gill is a senior data scientist and software engineer at H2O.ai, and Patrick Hall advises us on responsible machine learning at H2O. Before I hand it over to Navdeep and Patrick, I'd like to go over the following housekeeping items. Please feel free to send us your questions throughout the session via the questions tab in your console. We'll be happy to answer them towards the end of the webinar. And this webinar is being recorded. A copy of the webinar recording and slides will be made available after the presentation is over. And without further ado, I'd now like to hand it over to Navdeep.
Great, thanks, Patrick. So like Patrick mentioned, this talk will be about a deep dive into responsible machine learning with driverless AI. So the goal of this talk or this webinar is to essentially give you guys a brief overview of sort of the methodology that we use at H2O and specifically use in driverless AI based off of previous webinars that we have done, and then sort of jump right into the product itself to kind of showcase how one can interact with MLI and driverless AI. So we'll quickly go over some background. So in previous webinars and previous talks, you guys have probably seen that, transparency and accountability, trustworthiness, those are all important things when it comes to applying AI and machine learning, especially in regulated industries like banking and insurance, but also, it should be strived for in any type of industry where a decision can affect someone's life or can affect some important outcome. So these are sort of things that everyone should try to strive for. But specifically in regulated cases, a lot of people are already doing this, and the goal of this webinar is to kind of showcase how one can enable AutoML tools to sort of go about this in a responsible manner. So, like I said, transparency, accountability, trustworthiness, those kind of all tangle into this concept known as responsible AI. So we'll discuss that in the next slide. So responsible AI is sort of the idea that you use technology or in this case, AI and machine learning in a very responsible manner. You're trying to go about things in a transparent manner. You're trying to account for all of the decisions that are made, and we sort of break this down into 6 categories. So there's this concept of explainable AI, then there's interpretable machine learning technology, there's ethical AI, secure AI, human-centered AI, and compliance. All of these components come together to build this concept known as responsible AI. So, in the last few years, we've seen a lot of failed cases of AI being deployed in real life, causing a lot of issues for many people, causing a lot of issues for certain industries and certain companies. So the idea with responsible AI is we want to kind of mitigate these types of risks and sort of avoid any type of biases or any type of irresponsible use of AI in your applications. So, like I mentioned before, we sort of break responsible AI down into these 6 components. So we have explainable AI, which is the ability to explain a model after it has been developed. We have interpretable machine learning, which is utilizing transparent model architectures and sort of making the ML process a little more intuitive for either practitioners or people who are having these models applied to. There's also ethical AI, which is, you want to achieve some type of fairness in your machine learning predictions itself. So, for example, you don't want to have any bias when it comes to certain demographic variables for your machine learning application. We also have this concept known as secure AI. So this is about debugging and deploying ML models with certain countermeasures against cyber threats or having your model hacked or anything of that nature. And next, we have human-centered AI. So this has to do with in any application that utilizes ML, you kind of want to have a human component to it so people can interact with it. The results that come to them make sense. and there's no ambiguity going on there. And the last thing about responsible AI is sort of making sure that your AI application is compliant. This can be usually for regulatory compliance, so like GDPR, CCPA, et cetera. These type of regulations play a huge role in responsible AI for a lot of different industries. So, like I mentioned, all that comes together to sort of make responsible AI the explainable aspect, interpretable machine learning, security, ethics, compliance, the human-centered aspect if you're making AI applications, things like that. All of these components come together to make this big field known as responsible AI. So with this webinar, the idea we're trying to tackle, or the question we're trying to tackle is, can we utilize sort of these new AutoML tools to go about machine learning in a responsible manner? So at H2O, we think the answer is yes. Of course, we can't provide any compliance advice. That's not something we're obligated to do or something we're qualified to do. But we do think that you can utilize AutoML tools in a responsible manner. And specifically, we're talking about H2O Driverless AI, which is a AutoML system that helps visualize data, helps feature engineering, model training, and we also have the MLI component built in as well. So the one key thing about AutoML systems is sort of like you would expect, it should boost productivity. You should be able to tackle various problems without much manual tuning of the models, without much programming of models, things of that nature. That's sort of the goal of AutoML, is you want to iterate very quickly with a lot of different experiments. And with Driverless AI, you're sort of enabled to do that. So here's the brief agenda that we'll go over today. I'll sort of go over a brief intro, go over, the why, the what, and the how when it comes to responsible machine learning, and then hopefully show you guys the tool itself to see what you can do today. So first, terminology that we'll try to introduce is machine learning interpretability. So this is the ability to explain and present in understandable terms to a human. That's the quick definition, and of course there's a resource there as well. The next term is AutoML. So in this case, it's Driverless AI. It's not an open source tool it's our closed source tool that we offer. And built in Driverless AI, we have MLI, which is machine learning interpretability built into this AutoML system known as Driverless AI. So this is the typical data science workflow. So you see here, we have the data integration and quality, feature engineering, model training, and then machine learning interpretability comes usually at the end. This has to do with disparate impact testing, so that's about fairness, sensitivity analysis, which has to do with model debugging, looking at feature importances, reason codes, surrogate models, partial dependency of features, model documentation, which is quite popular in regulated industries. So as you can see in this type of workflow, machine learning interpretability comes at the end. However, you can build a responsible machine learning workflow throughout the entire process, not just at the end when it comes to explaining what a model is doing. You can build out constrained features, do constrained type of feature engineering. You can build interpretable models yourself in Driverless AI. So all of this can be achieved today with AutoML tools. So it's not just something you think about post-hoc, it's something you can think about throughout the entire process. So here we'll go over why it matters. So this slide is sort of showcasing what people previously thought about white box models versus black box models and how there's a performance trade-off. However, we're seeing that's not really the case nowadays. There are very accurate models that are very understandable. For example, GA2M is a specific model. We of course have experimented with explainable neural networks, which is another type of accurate model that's also explainable as well. So we're seeing today that this trade-off is sort of diminishing over time. So like one thing you could see if you were to look at, let's say, the trade-off is with, like, for example, linear models versus very complex models, is with linear models, you can get exact explanations for approximate models, and then with machine learning models, you can get approximate explanations for exact models. Like I said, this is not the case all the time anymore. It still exists in certain cases. There are going to be models that are more black box versus white box models, and they will be more accurate. But it's just a matter of kind of finding the balance between the two, if that is the case. And also, there are interpretable models out there that can achieve great accuracy, while at the same time holding on to interpretability. One thing to also consider is the multiplicity of good models. So, there could be many models that sort of fit your use case. So a lot of times, what you want to do is you want to pick the model that is not just only accurate, but you also want to keep interpretability in mind. So it's just getting, the 0.001 in AUC is not enough. You have to see what the trade-off is in terms of the complexity versus the explainability of the model itself.
Hey, Navdeep, can you hear me?
Yeah.
Can I chime in real quick?
Sure.
So just really quickly, we've been thinking about this idea about the multiplicity of good models for I don't know, about a year and a half now. And I just ran an experiment because I'm a huge nerd, maybe over the weekend, where I trained something like 200 just regular black box MLP neural networks. And I looked at and totally random grid search, nothing special, just trained 200 different neural network models on some simulated data. And so in addition to interpretability, I was also measuring a fairness metric known as AIR, adverse impact ratio. And if you look across those 200 models, it was easy to find models that were both accurate and had good adverse impact ratio numbers. So Navdeep's exactly right. There are a lot of different good models. Some might be interpretable, some might be accurate, some might be fair, some might be all three of those. And I think it's really just a matter of looking. So I wanted to sort of piggyback off what you were saying, but also in terms of fairness. And then I need to give my friend and colleague Nick Schmidt credit for this idea, because it's, he was the first one. I'm not sure it's his idea, but he was the first one I heard talking about it. So there's lots of good models out there. Some are interpretable, some are fair. Why not choose those? Okay, and I'm being quiet.
No, great. Thanks for saying that. Of course, backing me up on what I was saying. That's always good. So the next concept we're going to go over in this intro is about fairness. So, fairness is essentially ensuring that your model is not discriminatory in terms of gender, age, ethnicity, anything of that sort. This is particularly important for regulated industries. So you're going to hear that come up a lot in a lot of regulated industries. This is the kind of thing they want to avoid, because a lot of times those models that they're deploying affect people, and they affect them in terms of financial gain or anything of that sort. So you want to ensure that you're not introducing any bias. So this is one concept that I would like to go over briefly. And of course, in Driverless AI, the MLI module, we offer a way to test for this as well. So the next thing you want to see with machine learning interpretability is this concept of trust. You want to ensure that the model itself is performing to your expectations based off of your domain knowledge. So you want to see the sort of the sensitivity of the model to certain inputs. You want to see when the model starts going, let's say, haywire, and when the model does not perform as well as you would like because the inputs don't make any sense. So you can see here in this sort of graphic that's on the screen now, and you can see that the model might be pretty stable for a certain range of the data, because that's what it's on the training. But then once you got out of the training set, it starts making these wild outputs, which don't make too much sense. So this is something you can easily test for just by debugging the model itself, by using sensitivity analysis. So, adding in certain inputs and seeing how the model reacts. This is a good way to see how your model might do in real life if some data gets in that it did not see during the training set. So the next thing I want to go over is this concept of security, and I think Patrick, he might be able to chime in after I go over it briefly, because he's done a lot of work in this regard. So with security and hacking, we see this a lot in certain traditional software, and it's sort of glossed over in machine learning, in my opinion, and it's glossed over when it comes to the deploying machine learning models. But in reality, we should treat this in the same way. When this machine learning model is deployed, it's a piece of software that's used to make automated, output and decisions for people or for companies. So we want to ensure that we're not vulnerable in that regard. So, we want to debug the model before it's deployed. We want to ensure that certain features from the model cannot be taken out by using surrogate models. And for example, an attacker can maybe, and this has been seen in the literature, an attacker can sort of use a surrogate model to kind of recreate the original training data set as long as they can get their hands on the predictions. So this is something we want to ensure that we're not introducing, and it's something that should be taken seriously before a machine learning model is deployed.
Yeah. So I'm happy to chime in whenever you're done. So everyone on the call should know, Navdeep and I are, he's on the West Coast and I'm on the East Coast. I can't see his mouth and I don't know when he's done talking. So just if you're done, I can give some color commentary, Navdeep, but if you had a few thoughts. Okay. So there are published hacks on machine learning models, and I can't say whether or not this is something you should be really worried about today. It's definitely something you should be aware of and probably be prepared for today. And Navdeep did a pretty good job describing a lot of the attacks. A lot of the attacks are not going to look like traditional cybersecurity incidents. They're just going to look like high usage of your model API. But you may be thinking, well, what can someone do? And Navdeep brought this up too, and it's called a membership inference attack. It's probably the most damaging kind of attack. Just by pinging your machine learning endpoint, lots of times, someone can extract your training data with no other information than just random just random inputs to your API and the prediction that comes out. And these can get you in trouble with existing cybersecurity regulations in the U.S. And another thing I'd urge, two more points on this. Another kind of attack is an insider attack. This is like if I went to go work at like a early stage fintech and planted some data in their training data that say made my girlfriend's mother get a huge loan, right? And then when she gets the huge loan, we just all disappear, because my partner's Korean, and so we just all disappear back to Korea or something with all your fintech money, and that would be known as a data poisoning attack. And my last sort of point here is whether we're worried about fairness, or whether we're worried about security, or whether we're worried about model drift and instability. Why in God's name don't people have incident response plans for AI? I mean, it just makes no sense to me. What other technology do we walk around talking about how serious and important it is, but there's no incident response? There's not even a notion of what incident response means for when something goes wrong with your AI. So this idea of incident response is another thing that we can sort of borrow from traditional cybersecurity and is probably extremely valuable in machine learning and AI. All right, and I'm going to be quiet now.
Great. Thanks for applying that. A lot of extra detail there that I missed out on. But yeah, like Patrick mentioned, security might not be the most important thing now, but it's something to always keep in mind, because when these models are deployed, sometimes we can't control for every single thing, so we need to have some sort of safety harness that we can rely on to avoid any pitfalls when it comes to security, when it comes to fairness, anything of that nature. So the last part of the intro, I believe, is the sort of regulated and controlled aspect of machine learning interpretability. In regulated industries, there's this legal requirement to kind of ensure that the model is performing to a certain standard. You need to have some type of explanation for why a certain decision was made. These are known as reason codes. So a simple example is if you're denied credit somewhere, the lender has to tell you, what were the top, like, I don't know, 4 reasons for why you were denied. Kind of give you, first of all, the reasoning behind the decision itself, and also I like to think to give you some information on how you can improve this situation in the future. What steps can you take to kind of make yourself more attractive to lenders so you can move on and take that next step. And of course, security is also part of the regulation because these decisions affect people and they're in a regulated environment. A lot of times they have to do with financial gains and things like that.
And the data privacy aspects of this.
Yes, exactly. So a lot of those are very important and regulated in controlled environments, and all in all, more reason to think about machine learning interpretability and responsible AI.
And one thing I'll add, so if you're working in financial services, none of this is surprising to you, but for some people outside of financial services, maybe healthcare, maybe HR, some of these things might seem a little new. And one thing I'll add is, yes, you do need to be aware of these sort of pre-existing regulations in the United States and at the state level today. But in the midst of the pandemic, in the midst of the recession/depression, the FTC, Federal Trade Commission, publicly releases a letter in April saying they're going to start, basically hinting that they're going to start looking into just general enforcement of AI best practices. So you can Google that. It's on the web. It's a public letter from the FTC saying, we're going to start looking into how companies in general are using machine learning. And that is just one of many, many sort of pending regulations. Now, people say it's going to be slower to happen in the U.S. than in Europe or in Singapore, where it's already happening. But to that, I'll reiterate that even the Trump White House has put out AI guidance, and also that states' attorneys general can enforce local laws on companies using machine learning and AI. So this compliance thing is very real, and likely only to get realer. And I'm going to be quiet now.
No, that's great you brought that up. Yeah, I agree that the compliance aspect is going to just start harping on more and more industries, as time goes on. As machine learning and AI is used in a sort of daily basis or across different industries, some type of regulation will have to be put in place. So it's better to be prepared now than to be not prepared at all and be surprised by everything later. So in summary, responsible machine learning, matters a ton. You need to find some balance between the performance of your model and the interpretability of your model. You need to consider multiplicity of good models. Some models might be very accurate but not interpretable, while others might be the inverse, and some might be everything in between. So sort of looking at these models and figuring out what's best for your use case is always key. You have to keep in mind sort of the fairness and social aspects of machine learning, the trust of the model, consumers and producers, security, regulated, controlled environments. All of these play a big role in responsible machine learning, and frankly, they all matter a great deal. So next, we'll go over sort of what's needed to build out responsible machine learning. Build out human-centered low-risk models with driverless AI specifically. So here we can the first thing you want to do is sort of load your data in a type of machine learning workflow. So in any machine learning workflow, the first thing is to do some EDA. So here's a screenshot of sort of the EDA you can do with driverless AI today. Let's see if I can sort of show. I ran some experiments. So I kind of want to, instead of showing the screenshots themselves, I think it would be great to kind of show you guys sort of the application. So here we're in driverless AI right now, and we're looking at the data sets. And to see that screenshot that you just saw, I can go to details. And then this data set itself is a credit card data set. So the target in this case is you're trying to predict the probability of default next month. So it's a binary outcome. And then in this initial page, you can sort of see the breakdown of each column. how many females versus males do you have, education levels, marital status, distribution of age, payment statuses, were they delinquent in the previous month, or were they 2 months delayed, 4 months delayed, etc. And it's just looking back at the previous month's payment history. You can look at how much they were billed and how much they paid, their balance for their credit card. So, the first key thing in any machine learning workflow is to look at your data. And in responsible machine learning, it's the same thing. You want to look at your data. You want to visualize what your data is doing. These all play a lot of important factors. So here, it was just, this is a screenshot what I was just showing, and of course we can visualize data itself. So in Driverless AI, you can look at things like correlation plots, histograms, like skewed histograms, gap histograms, box plots, look for outliers. All of these types of things are available today in Driverless AI. So this is just an example of a correlation graph that I picked up earlier. So you can kind of see how all of these variables in the credit card data set that I just showed are related to each other in terms of correlation. And of course, you can download these plots for later, for any report you have to make, things of that sort. And this is sort of continuing on the different type of other plots you can see, like outlier plots. So there might be outliers in certain variables. These are things you should account for during your initial phase of exploring the data and visualizing the data. So in Driverless AI, this is all built in and it's automated. So there's no need for any manual effort from you at that point. So the one key thing that Driverless AI offers versus other applications, I think, is the ability to do feature engineering. And you as the user can control the level of feature engineering that is done in a Driverless AI model. So Driverless AI, usually when you start an experiment, there's these 3 knobs, accuracy, time, and interpretability. In this screenshot here, you can see I've set it down to the interpretability level is set to 1. So this is going to do, a lot of complex feature engineering. And so that you can think of this as sort of this black box type of feature engineering, where the features themselves can be quite complex and they might not be very straightforward to understand. Of course, you can increase this to 10 as all the knobs go from 1 to 10. You can increase this to 10, and what this does is this ensures that the feature engineering that is done is understandable to any user or to any person that is interacting with the model itself. There's also a few other things you can do with feature engineering. So you can of course utilize the interpretability knob, but then you can also go into the expert settings as well to deal with monotonicity constraints. So you might know that a certain variable should be either positively correlated to the outcome or negatively correlated to the outcome, and you can control the monotonicity constraints yourself in the experiment setting. So I'm going to sort of go into the experiment now that I had earlier. And then, of course, you can go to the experiment page, go to new experiment, and I can select the same data set again. And then in this case, you can, of course, select the columns you do not want to use in the model. So, in this case, since we want to ensure we're not using any demographic variables, so we can drop these 4. They will not be utilized in the model itself. And then we can select our target, which is the probability of defaulting next month. And sort of these are the 3 knobs that I was mentioning. So in this case, I can do something like, to set the interpretability to 10, sort of utilize simple feature engineering, nothing too complex. We can go into the expert settings ourselves. And then here you can utilize a lot of different things. There's a lot of different parameters you can tune. But if we go into the models, you can sort of look at the different type of models you can utilize. So you can actually turn this on to a lot of interpretable models that you want to use. So like stick with the GLMs, the DT models, rule fit models. And then one thing I like to mention is there is a monotonicity constraint that you can set for certain variables. So that's always important if you know that there's a certain relationship going on with the outcome and the inputs themselves. So that's something you can take advantage of within the expert settings. One thing you can also do within the expert settings is sort of blacklist certain transformers. So if you deem a certain feature engineering to be too complex, you can also black box these or blacklist these feature transformations so they're not utilized. So this sort of gives you the opportunity to utilize an AutoML tool, but also control for certain things that you do not see fit for your application. So, like I said, you can sort of balance between the accuracy and interpretability of the models themselves. Between black box models and white box models, you can try to find the middle ground by utilizing constrained feature engineering and also utilizing monotonicity constraints if you're aware of these type of relationships. And you can also utilize interpretable models themselves, which are built into Driverless AI. In addition, we also offer, or there is a way to look at custom recipes for Driverless AI. So this is, if you're familiar, this is a way to kind of bring in your own model itself. And what we've done, the MLI team, is we've put together a couple interpretable models. So we have this GA2M model, which is a sort of interpretable gradient boosting machine. Based off of it's based off of the original GAM model. It's just another version of that with boosting, and so you can utilize these custom models in Driverless AI itself. And we also have explainable neural networks, which have been made into a recipe as well. So these two we've put together, and we're continuously adding more. And you yourself can add more interpretable models to this repo to utilize for future experimentation. So this is something we have put together to kind of bring the point home that you can utilize these new interpretable models that are coming out in Driverless AI. So you're kind of extending the AutoML tool of Driverless AI with your own models themselves. So then here's sort of a breakdown of the different, what each knob would mean in terms of feature engineering and monotonicity constraints and what type of target transformation would happen. So as you can see, as you increase the knobs, you're getting more complex type of feature engineering occurring. As you decrease the knob, the feature engineering is going to get a little more simpler. So for example, here, we can sort of turn on like the GLM model and turn off the light GBM model or make it auto. All these things are available to you to tune with depending upon your application. Like I mentioned before, we have built-in interpretable models, and we also have the ability to bring in interpretable models based off of either your own application or the couple applications we have put out there so far. And then this is just showing how one can go to the expert settings like I was in before and sort of turn on and off different models that they want to use. So in this case, you only want to use, let's say, the XGBoost GBM. You can do that within the expert settings themselves. We also offer a mode called compliant mode, which is probably going to be really popular for any type of responsible machine learning application. The idea here is that the interpretability. So compliant mode can be set through the expert settings, and the idea is that the interpretability will be forced to be 10, which is the highest level. It only utilizes GLM and rule fit models. It only treats some numerical features as categorical. There will be no ensembling. The interaction depth for certain models will be set to 1. There'll be no target transformation, so the target will always be seen in the space that you're used to seeing it in. So there's also this one-click way of getting some type of compliant mode. And of course, we offer a traditional model assessment and diagnostics, which is offered in driverless AI. So as the experiment's running or once it's finished, you can look at things like the ROC, lift, gains, KS chart. You can look at a summary of the model in terms of performance. In terms of the assessment, you can also look at final, sort of this model documentation that you can download and look at, which sort of gives you a very detailed overview of what actually happened in the experiment. So this is very important for regulated industries, and it's also important just to document your models themselves to see what happened over the course of your machine learning endeavor, so you can share this with your teammates or other people in your organization.
And again, sorry, I'll try to be quick, but again, you may be thinking like, oh, it's so boring to document my models, but all valuable enterprise software resources, are typically documented, and they should be documented. But another more crucial sort of rubber hits the road issue here. Let's say, you wake up one morning and, like Apple and Goldman Sachs, you find yourself on the front page of newspapers saying that you're being discriminatory. If you want to try to fix this, if you want to call people in to try to fix this, they have to know the baseline. Like, when was your model behaving properly? When did you think it wasn't discriminatory? When did you, so that there's some kind of understanding of what it's supposed to be like and what it is like now, so that we can somehow think about getting it back to the way it's supposed to be. So again, the model documentation, it is boring and it is tedious. Driverless AI makes it very, very easy. But just in general, it's really important for when things go wrong, right? I see so many people hyped up and excited about machine learning and AI, and of course I've devoted my career to it. But once you start thinking about when things can go wrong, right, that's when model documentation and interpretable models start to be really important, so that you can debug what's going on. And I'll leave it at that. I'll get back down off my soapbox and shut up.
Yeah, just to reiterate, the model documentation does come off as boring, but it is very important to sort of, see what happened during the course of any machine learning application you're doing, and to sort of have a way to debug any issues down the road. And then in addition to the model documentation, you can also do traditional diagnostics as a part of the assessment in driverless AI. So like I mentioned, these steps that I'm showing, they're all built into the application. There's nothing I'm bringing in from the outside world into the application itself. It's all built in, and it's all ready to go once you start doing an experiment or anything of that sort. So once you've done the assessment, then there's these next 3 steps that you can sort of go down the road with in terms of MLI. You could do the post-hoc model debugging, so this is the sensitivity analysis, or in other words, what-if analysis. You can look at post-hoc explanations, so reason code. So this could be done for a subset of data. It could be done globally, for the entire data set that was used, or it can be done locally for a specific row. You can look at post-hoc bias assessment. So this is the disparate impact testing that I mentioned before. These 3 steps are built into driverless AI today. And then, of course, once all of this is done, there's sort of this human review that has to happen at the end. So this is where you as a data scientist or an analyst come in and sort of see what the results are, see if they make sense to you. And since this is an AutoML tool, a lot of these experiments can be done rather quickly compared to what has been done in the past. So that's sort of the time benefit that you're getting here. So you can focus more on the science itself. You can focus more on your application. and which is the more important part in my opinion, instead of focusing more on the tuning of the model, which is taken care of by Driverless AI. So in this next few slides, we'll sort of go over what MLI has to offer today in Driverless AI. And then this is sort of the iterative loop that one would go through in Driverless AI when it comes to responsible machine learning. So like I mentioned, you have your EDA, feature engineering, you have your models, you have some assessment, which is the model debugging explanation, looking into bias, model, or having some human review, and then of course, then you deploy your model once you're happy with everything. So here is sort of a few screenshots of what MLI has to offer today. So I think for this part, I can sort of go into the application itself. Let's see here. So we'll go back to that same experiment that I ran before, which was on the credit card data set, and we can go to interpret this model. So first thing you would notice is that this is a new UI that we have built for MLI. So this, compared to previous versions, if you've seen them before, this is sort of has these tiles. So this is a brand new revamp. So you can look at each thing individually, and they're broken down into 3 sections. First thing you would get once we interpret a model is you would get the summary. So you would see sort of what experiment MLI was applied to, what was the target column. You get all this summary information about the target itself, any type of target transformation that occurred, the feature space for the surrogate model, which by default is the original features, the surrogate model CV folds, the line method that was used, the variables used to cluster in K-line, the tree depth, and then of course here you have the feature importances for the Driverless AI model itself, and then you also have performance of all the surrogate models that have been built. And then you have, for one of the surrogate models, which is the surrogate random forest, you get the feature importance of the original features. So this is what you initially get from MLI from a summary standpoint. You'll see all this information always on an MLI page. Then we can jump into the Driverless AI model itself. So you can look at things like, so this is, you can look at the typical feature importance from the Driverless AI model. So as you can see, the most recent payment status is very important for this model, which somewhat makes sense. You would expect, the model picking that up as a very important feature. We could look at the transform feature importance. So, out of the transform features, which one was the most important? So the model I ran was quite simple. So, this is still in the original space, but of course you would expect to see this in you might see more complicated features here, feature names that you don't recognize because Driverless AI made them. That can happen if you build a very complex model. One new thing that we've added in the next release of MLI is the ability to get Shapley values for original features, and we utilize kernel Shapley to do this, which is a sort of combining line with the Shapley approach. So this is a very nice way to kind of see what the important features are in their original space, which should be features that you understand pretty well. And then this can sort of drive home reasons behind why certain decisions were made. Of course, you can still look at the transform Shapley. So you see a theme here that you get, the original feature importance transformed, original Shapley, transform Shapley. We also offer partial dependency plots for the Driverless AI model itself. So this is sort of looking at the average prediction across different levels of a variable. So in this case, we can look at page 0, which is the payment status. You can see here that payment status is in -2, -1, 0. You sort of follow this path, and then once you hit 2, which I think you're 2 months late, you sort of see this jump that happens in the average prediction. You can also cycle through and look at different variables. We usually pick the top 10, but this is configurable itself. And of course, you can sort of you can sort of select a row, which should give you this aspect of the PDP plot, which is individual conditional expectation. So this is how does this particular row behave if you toggle with the different inputs. So these are sort of what's offered with the Driverless AI model, and in addition to that, we have the disparate impact. So this is sort of looking at the fairness itself. So one thing that you probably saw in previous when I was building out this model is I didn't use certain demographic variables. So we can look at, like, for example, the variable of gender, and we can say the reference is male, and then we can sort of look at, based off of that, you know, are we achieving any fairness when it comes to comparing females versus males? And it looks like for the most part we are. So if you look down here, we offer things like looking at the confusion matrix between males and females in terms of this binary classifier. You can look at different metrics like adverse impact, accuracy, true positive rate, etc. You can look at marginal error and standardized mean difference of the predictions. And then we also break it down in terms of differences. So in this case, you don't really see either a small, medium, or large difference between the two. Everything's pretty acceptable. We also don't see any disparity happening with the thresholds that are put in by default. And then this right here is just the group parity. So what this is looking at is, does this value fall within the threshold? And in this case, it does, so you get a true. And this logic is done throughout the entire application. So we can, of course, toggle and look at things like marital status. And then we can compare everyone to the level of married. One thing you might notice here is some of these are out of range. So you see that some are falling out of range here. And usually, in this case, it looks like other is falling out of range. And this could be due to the fact that it's a very small sample. So this is a quick way of seeing that, oh, you know, this level was not represented well enough in the data set. So it's something to keep in mind. This may or may not be a problem for you. It all depends on the application. So this is just something I've noticed with this particular data set. The next thing we have here is for the Driverless AI model itself is we have sensitivity analysis. So this is a way to sort of debug your model and see how it behaves when you toggle with certain inputs. So for example, I can go in here, let's say the pay 0, and I can set everything to, let's say, 2, and then I can rescore. And then I can see how the probability of default changes. So in this case, you see it went up by about 0.32. That's a huge increase. That's because I've made everyone pretty much default. And you see the model is sort of, you know, reflecting that itself. And this tool is sort of, you can, if you're familiar with Google's What If tool, it's very similar to that in that regard, that you can go in here, it's sort of a playground for your model, and you can try out different scenarios and see how your model reacts. So this goes back to the model debugging aspect of responsible machine learning. And then, of course, we can go here and we can sort of reset everything back to the previous, and then we can see this chart up here sort of breaks down where the positive cases, where the negative cases, and then we have the F1 cutoff here, and then we have sort of the summary rows. Summary rows, basically a typical row you would see from this data set, and where that lands. So this is stuff that's available to you today, and this new UI will be available in the next major release of Driverless AI. And quickly, we can jump into the surrogate models that we have to offer. So in previous webinars, you've probably seen that, you know, we have the K-line plot. So this K-line plot here is sort of looking at this particular row, but we, of course, we can clear it out and we can look at it from a global perspective. So, you know, this is a global GLM surrogate model built to the predictions of the Driverless AI model itself. we can go into looking at the explanations. So in this case, the explanations are broken down globally. So this is just a global overall view of the reason codes and how they affect the outcome. We can sort of select a certain row and then look at the explanations. And this page gets even longer because now you're looking at local reason codes. And then since it's K-line, it has to do with clustering data and building subsequent GLMs in each cluster. So then you get the cluster reason codes, and then you get the global reason codes below that. So these are all available within the surrogate model tiles of MLI. We also have a decision tree surrogate model. So this is a single decision tree built to the predictions of the complex driverless AI model. And then you can look at what path your particular row went. You can look at globally, what's the model flow, what are the type of rules that you can kind of see this model is taking on. And of course, you have to keep in mind the accuracy of the model itself when you're looking at these rules. So if the surrogate model is quite accurate, then the rules might be a good thing to look at and kind of figure out what your model's doing. And of course, I mentioned we build a random forest surrogate model. So for that particular surrogate model, we give you the feature importances, the partial dependence, and we also give you the legal and covariate out importances. So these are all built into the application today. These are all built into the application today, and this new UI will be available in the next upcoming release of Driverless AI. Let's see here. I think we're at the 10-minute mark. Do we move on to questions now, Patrick, or?
Yeah, it looks like there's some good questions that we could spend some time on. So why not? And
okay.
I'll just, or go ahead, Patrick.
I'm happy to read the questions off if we just want to go in chronological order here. First question, can you explain more about the multiplicity of good models?
Yeah, I mean, I can try. And Navdeep should feel free to chime in here too. Machine learning training is very over-specified and degenerate, right? There's just a million different combinations of rules and parameters that can get you a good model for most data sets, for a data set of, sort of any decent size. And now I've got my 18-month-old here. He's very interested too. And this is also known as the Rashomon effect. And so if you want to Google and get some more serious math, that's what I would Google, Rashomon effect. And basically, this is a blessing and a curse. I think people have pretty much only looked at it as a curse in the past, right? I have so many good models to choose from. How do I pick one? And then it leads to kind of model selection issues, but as Navdeep and I were talking about, in the context of fairness and interpretability, it can really be a plus, because if you don't care about that last decimal point of AUC, which I don't know why you would, because real world isn't a Kaggle contest and your data is going to drift and you're just going to be overfit. If you don't care about that last decimal point of AUC, then you're going to have dozens of models to choose from, and it's very likely that if you look at these models, you'll find ones with good fairness characteristics and likely good interpretability characteristics. And to give you some idea, we've done some experimentation, and it looks like for this sample data set that Navdeep is using with about 23 columns, there's at least 500,000 accurate, models with roughly the same AUC for this silly data set. So of those 500,000 models, there's going to be a large diversity. And I hope that sort of answers that question about, tell us a little bit more about the multiplicity of good models. The one last thing I'll add is it was coined by Leo Breiman and he has a really good paper from 2001 called Statistical Modeling: the Two Cultures, and that would be another good thing to Google and look up and learn more about the multiplicity of good models.
Great, thanks for that. Next question is, what are your favorite criteria for choosing best models? And there's a couple of examples like AIC, ROC, AUC, RMSE, accuracy, etc. You wanna go for it, Navdeep?
So, yeah. So sorry.
You want me to get up on my soapbox again?
So the question was, what's your favorite criteria?
Yeah.
I don't think I personally have a favorite criteria per se. I mean, I guess in the past, when I was like naive and in college and learning about machine learning, I thought AUC was the greatest thing for finding classifiers, and RMSE was the greatest thing for regression. But as I've been looking more into responsive machine learning, it's not really about the specific metric. It's more about, first of all, what's your application? Kind of what are you trying to achieve? Are you trying to explain some phenomena? Are you trying to predict some phenomena? You don't care about the explanations, which sometimes I guess happens. Or if you care about explanations and you care about accuracy, then you kind of have to, balance the two. So in terms of accuracy, you can look at certain metrics like AUC, RMSE, things of that nature. But in terms of explanations, you can do some of the methodologies that we've been showing. So you can look at the feature importances globally. Does that make sense based off of your domain knowledge or what you've learned about this particular problem you're trying to tackle? You can look at partial dependency plots to see how is your model behaving and when certain inputs are changed. And the same applies to sensitivity analysis. If you're in a regulated industry, most likely disparate impact is probably pretty important, especially if you're dealing with anything in finance or lending. So that has to be kept in mind as well. So, you can have a very accurate model, but it's failing the disparate impact test, the simple disparate impact test. So then it's not a very good model anymore for your application. So I think those two have to be kept in mind.
I totally agree. And all I will add to that, right, you should be considering a lot of different accuracy metrics and a lot of different fairness metrics. And all I will add to that is there's a really brilliant paper by Rich Caruana from 2004 when he was in charge of the KDD Cup, where instead of just looking at a leaderboard, with just like AUC 0.998, AUC 0.997, AUC 0.996, okay, the one with the highest AUC is the best model, he actually looked at the rankings of the models. So I'm going to look at, that highest one is rank 1, rank 2, rank 3. He looked at those rankings across different folds of a test data set. And, that ranking, if it's a small test data set, will shuffle a lot, right? What's the best model in fold 1 might be the 14th best model in fold 2 or something like this. And so this idea of cross-validation combined with ranking, that's my favorite way to pick a best model. And you can do that with both accuracy metrics and fairness metrics to get some idea of a more realistic version of ranking your model. So Google it. It's Rich Caruana 2004 KDD Cup results.
Great. I think we have time for one more question here, reaching the top of the hour. So we'll go with, how does driverless AI handle missing data?
In terms of missing data, driverless AI will try a lot of different imputation techniques. Most likely it's doing a lot of imputation techniques that is trying, so it can be mean imputation, and I can try to provide more details after the webinar, after I do my own research.
Okay,
well,
maybe,
I think a lot of the models, really quickly, a lot of the models in driverless AI are tree-based, right? And so tree-based models, they don't care if, the models we use don't necessarily care if a variable is missing. It's just another level of the variable that the split search considers. When we're using models with weights or parametric models, I think, Navdeep's right. I think we do a lot of sort of fancy imputation, but we better look that up after and follow up afterwards. And I'll be quiet.
Okay. Well, I guess that'll do it for questions today. Definitely want to thank Navdeep and Patrick for taking the time for the presentation. I'd like to thank everyone who joined us as well. The presentation slides and the recording will be made available on our BrightTalk channel later today. And we hope you have a great rest of your day.